Hello there. In this video we're going to investigate some particular infinite series that can be represented via the Riemann-Zeta function. So recall the Riemann-Zeta function, zeta of x, is defined to be equal to the sum from k is equal to 1 to infinity of 1 divided by k to the power of x. In particular, there are some special values that some people know, for example, zeta of 2, which is equal to the sum from k is equal to 1 to infinity of 1 over k squared. So 1 plus 1/4 plus 1/9 plus 1/16. It can be proven that this is equal to pi squared over 6. We haven't proven this yet in the series, but we will eventually once we have a couple really neat tricks to prove this. But this is often referred to as the Bessel problem. And a related function to the Riemann-Zeta function is the Dirichlet-Eta function. So remember the Dirichlet-Eta function, eta of x, is equal to the sum from k is equal to 1 to infinity of -1 to the k plus 1 divided by k to the x, which is the alternating Riemann-Zeta function, if you may. And of course, we've already proven some values for the the Dirichlet-Eta function, namely eta of 2 is equal to the natural log of 2. So in this video, we're going to look at a couple of variants of the Riemann-Zeta function and figure out how to use them to evaluate particular styles of series. Alright, so the series that we're going to try and figure out is the following. So the first series I'm going to look at is the sum from k is equal to 0 to infinity of 1 divided by 2k plus 1, the quantity squared. So what is this series and what does it look like and how do we know it even converges? Well, this function can be compared to a p-series of p is equal to 2, so it can be proven that this does converge to something. So what does it look like? So when k is equal to 0, we get 1 over 1 squared. When k is equal to 1, we have 2 plus 1, which is 3 squared. When k is equal to 2, we have 2 times 2 is 4, plus 1 is 5. So we have 5 squared. So it's pretty much going to be the sum of all of the odd powers, reciprocals of 2. I'm going to call this series O for odd. And another series I'm going to look at is the sum from k is equal to 1 to infinity of 1 over 2k the power squared. So when k is equal to 1, we have 1 over 2 squared. When k is equal to 2, we have 1 over 4 squared, 1 over 6 squared, 1 over 8 squared, and so on. I'm going to call this series E, which again does converge by the p-series test. So notice that these two are pretty much related to the Riemann-Zeta function evaluated at 2. So we're going to use this to our advantage. Alright, so how can we figure out the values of O and E? Alright, so solution. So recall that zeta of 2 is equal to 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared plus 1 over 6 squared plus and so on. This series does converge by the p-series, so we know we can rearrange the terms of this and still have the same exact sum. So what I'm going to do, and of course we know this is equal to pi squared over 6, so from this, I'm going to rearrange. I'm going to look at my odd terms and also my even terms. So I'm going to have what? So I'm going to have 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus and so on plus 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared plus and so on. This must be equal to pi squared divided by 6. So this is my O series and this is my E series. So notice for my E series I have a common factor of 2 squared in each of those terms. So what I'm going to do is I'm going to factor out 1 over 2 squared from that entire series. So I have 1 over 2 squared times 1 over 1 squared plus, so I'm going to have 1 over 2 squared. 2 squared times 3 squared is going to be 6 squared, so I'm going to have 1 over 3 squared plus 1 over 4 squared plus and so on. This must be equal to pi squared over 6. So this value here, of course, is clearly zeta of 2, which we know is, again, pi squared over 6. So I have my O series is equal to, or O plus 1/4 of pi squared over 6 must be equal to pi squared over 6. So I have that O must be equal to pi squared over 6 minus pi squared over 24. So I'm going to get a common multiple by multiplying top and bottom by 4. So I have 4 pi squared minus pi squared, which is 3 pi squared over 24, which is the same as pi squared over 8. So what does that mean? So that means the sum from k is equal to 0 to infinity of 1 over 2k plus 1, the quantity squared, is equal to pi squared divided by 8. So that is our first theorem. So what about my E series? So remember, O plus E was equal to pi squared over 6. So now I'm going to solve for E now that I know my value of O. So that means pi squared over 8 plus E must be equal to pi squared over 6. So this implies that E must be equal to pi squared over 6 minus pi squared over 8. I can multiply this by 3 and this by 4. So I'm going to have that E is equal to 4 pi squared minus 3 pi squared over 24, which we know is equal to pi squared over 24. So what does this mean? So this means that the sum from k is equal to 1 to infinity of 1 over 2k, the quantity squared, is equal to pi squared over 24. Okay, cool. So we're going to do the same exact trick for an almost identical series, but we're just going to increase the power by 1. So we're going to consider the sum from k is equal to 0 to infinity of 1 over 2k plus 1, the quantity cubed. And we're going to be considering the sum from k is equal to 1 to infinity of 1 over 2k, the quantity cubed. So what is this? So this is going to be equal to, so when k is equal to 0, we have 1 over 1 cubed plus 1 over 3 cubed plus 1 over 5 cubed plus and so on. And this similarly is going to be 1 over 2 cubed plus 1 over 4 cubed plus 1 over 6 cubed plus and so on. All right, so again, I'm going to call this O and I'm going to call this E since they're both represent even and odd terms. So what can I do here? So recall that zeta of 3, which is 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed does exist. This is what we call Apé's constant, which at least at the time of making this video does not have a closed form, so we're just going to call it zeta of 3. So we have our odd terms, where's my dots there, okay, and also my even terms. So therefore, I can say that zeta of 3 is equal to O plus E, the even and odd terms of the cubes. All right, so from here, what do I know? So I can rewrite this as zeta of 3 plus O plus, I'm going to look at the even terms in more detail, so 1 over 2 cubed plus 1 over 4 cubed plus 1 over 6 cubed plus and so on. So I'm going to factor out a 2 cubed out of all these terms. So zeta of 3 is equal to O plus 1 over 2 cubed. So I'm going to have 1 over 1 cubed plus. So 2 cubed times 2 cubed is going to be 4 cubed. So that's going to be 1 over 2 cubed. 2 cubed times 3 cubed is going to be 6 cubed. So this is going to be 3 cubed plus and so on. And this is precisely Apé's constant again. So we can say zeta of 3 is equal to the odd series plus 1/8 times Apé's constant of zeta of 3. All right, so from here, what do we have? So our odd term is going to be equal to zeta of 3 minus 1/8 of zeta of 3. So that's going to be 8/8 minus 1/8. So that's going to be 7/8 of zeta of 3. So what does that mean? So that means the sum from k is equal to 0 to infinity of 1 over 2k plus 1 cubed is equal to 7/8 of AP's constant. All right, so what else do we know? So recall that AP's constant, zeta of 3, is equal to O plus E, and we already know what O is. So that means E is going to be equal to zeta of 3 minus 7/8 of zeta of 3. So at 8/8 minus 7/8 is going to be equal to 1/8 zeta of 3. So that means what? So that means the sum from k is equal to 1 to infinity of 1 over 2x, the quantity cubed, is going to be equal to 1/8 of AP's constant, zeta of 3. And you can probably even prove a mathematical induction property for the sum of even and odd powers of 2k plus 1 and 2k for, say, 4, 5, 6, 7, or pretty much any natural number n. Or maybe even if you're feeling real creative, you can consider any real number bigger than 1 to see if you can get a closed form for that as well. I definitely invite you. It's definitely possible. So pretty much what we've done here is we've just been able to look at a couple of infinite series that are pretty much rational function series and how to represent them in terms of the Riemann zeta function. Hope you enjoyed.